How do I? Oh, this one, this. Hello. Cool. Chat is working. Welcome everyone. So, where did we finish off last week? Or not last week, the day before yesterday. I think when we left the other stream the day, yeah, the day before yesterday. I think so. Um, we had an issue with just one more moment. Just one moment. Mm, mm. I just wanted to announce on my WhatsApp since some people check on that. Uh, okay, cool. Here we go. Last week when we stopped, we left it at I expect so the registers that we were working with, if I recall correctly, the registers that we were working with ended up not working the way we wanted them to work, if that makes any sense. Like the registers were not set up the way we wanted them to be, the way we expected the code to be. Namely, polarity was not set to low, phase was not set to low, and then the SSI software slave configuration. This is wrong, and we needed the SPE bit set. So I think it's SPI SPI. I think it's enable peripheral control. Yeah, SPI 2, SPI 2, and then this is enable. These are the two. This is what was missing. So first of all, I'm gonna quickly run you guys through the code that has changed. I don't know if you can see here. I'll just zoom in a bit. So I changed number one. I added to SPI.c. I added this line to SPI.c when doing when when doing the initialization. So I added this line. I think it's in initialization. Yeah. I added a line here to configure the data frame format. This we had a problem with because last time it was ending up being I think a 16-bit frame format, and we wanted a 8-bit frame format or something of the sort. And then also, as I was walking through the code, I realized that we had swapped through. We had uh, kind of set our defaults wrong. So high originally, if you look at my color coded, high was 0 and low was 1. So I had these two swapped around, and this is why we're getting the results that we're not getting. So I'm expecting that if we run this application now, we will get the settings that we expect, and then we can move on to implementing SPI interrupts. Cool. Just as a matter of testing. So let's test that our code is actually doing the thing that we want it to do. And by the way, you can leave questions, you can leave comments, you can join the Discord that's linked, and you can also leave questions there. And yeah, feel free to comment a question or live chat a question if that's what you need right now. So let's run the code. observe the registers and see if actually what we want is changing. If it is, then indeed we're on the right path, and we shall move on to implementing SPI. We shall move on to implementing SPI interrupts. Cool. Okay, so I will debug this as a STM32 application. I just need to see the debug console. Cool, debug console came up. And then I think I want to look at the SFRs and SPI GPIO init. I know GPIO init, we are initializing. So if we look at RCC, and then I think it's APB2 ENR, that's where IOs are. So IO port B is off. And if we run this, we should get IO port B enabled. Okay, so let's step through that. And IO port B is enabled. So now we're going to look get SPI2 initialized. We can actually check. We can start from here. I think SPI2 is going to be on APB1 ENR SPI2. So SPI2 is not enabled. So if I run that, if I run that line, a bunch of things will happen. Okay, let's look at what will happen. So number one, SPI2 is not enabled, number one. And then if we come down here to actual the SPI2 registers themselves and CR1, it's CR1 itself also has no, we don't have any its value is 0, so there's nothing in CR1. So what do we expect according to this? Number one, we expect that SPE serial port enabled will be 1, so we'll enable the port. Number two, we expect that the bus configuration will be full duplex. I think that's 0 for BiDi mode and BiDi OE, and then also RX only should be 0, and then the div should be 4, which we expect this to be, if it's div 4, I think it should be 2, and then DFF should be 8 bits, so DFF as well should be 0 for 8 bits. CPOL should remain low. C phase should remain low, and SSI should also not be set since we'll be using hardware slave management. So let's step through that code. If those settings are enabled, then we know that our initialization is working correctly since we're reading the registers on the device, and that should enable us to see that our code is working correctly. I will write out a fully fledged example where I'm responding to commands from the F4 device. I just haven't gotten around to it because I've been working on I2C and kind of like I've already tested SPI on the F4, which is kind of running the same code. So I know this code works, but some things could always break. Okay, so let's step through that and see. Cool. Awesome. So BiDi mode 0. BiDi output enabled 0. DFF, it's 1. Should be 8 bits. Should it be 1? Should it be 1? Should it be 1? SPI registers. SPI registers CR1. 0 8-bit for data frame format, 1 16-bit. So this is wrong. Huh? 0 8-bit data frame format, 1 is 16-bit. So what I see here is 8 bits. The data frame format should be 0, not 1. Okay. SPE is not enabled yet. That's because this is not working. So if we do step through that, we will get SPE enabled. Cool. But the data frame format is 1, and I don't think that should be 1. So, and then master 0, that's fine because we're in slave mode, the bus mode slave. C pole 0 low, C phase low. So I think if we go into our header file now, let's see if we made any mistakes with 8-bit and 8-bit, 8-bit 0, DFF 8-bit 0, DFF 16-bit 1. Cool. Now let's go back to SPI.c, and we need to know that we are actually setting the data frame format. CR1 DFF, SPI DFF, SPI config DFF. So in main, do we actually set SPI.dff, SPI DFF equal to that? Okay. So the other part where we could be messing up is in our definition of this macro. So this is bit 11 DFF. Bit 11, cool. So, and then what I am confused about is how come we get a 16-bit DFF even though we want even though we want 8-bit DFF. Ooh, there you go. Configure frame files, configure. It's done twice. So let's see if we don't do that twice. If we don't do that twice. If we don't do that twice. So device mode, cool. Okay. If we don't do that twice, do we get the right settings? Okay, cool. So I'm gonna go here. I'm going to save this, and then I'm going to run this code. No, I'm not. I'm actually just gonna run it completely. Oh, no. Here's the problem. If I run it, we don't get a debugger. We don't get a debugger. We don't know if it's actually set up. Cool. So welcome to Embedded. I'm good, Eric. Thank you for. Oh no. I am still streaming. Hey, Eric. I'm good. Okay, cool. For a moment there, I thought I lost my stream. So let's our SFRs. So we want to make sure DFF is working. Data frame format, cool, and SPI too. Okay, cool. So let's just jump through all the code that an init. So data frame format is still coming back as one. That's a problem. Somewhere in our initialization, we're doing something that is ensuring that our data frame formats come as one. I don't know why. That's fine. That's fine. It's in the init. DFF here. SPI config, SPI DFF. Push that there. Okay. I'm going to SPI.h and see define. And then if I go to sorry, I'm covering my mouth. That doesn't help when I'm talking. What if I set this as 0? Let's just stop and then let's debug that. So if we can debug that and we can find out why, we'll probably know. Cool. Yeah, so this is the other part of embedded development. So we basically have to sometimes walk through our code line by line and looking at registers to see if something is broken or to see if something works the right way. That's the other thing about embedded development. Like you don't have as many loggers and as many. Okay. Okay. Hmm. I don't know why the data frame format goes to 1, even though we set it to 0. I must be making some sort of mistake somewhere. I have no idea what mistake I could be making and where I could be making it, so that ends up as 1 rather than 0. It could be that SPI 2 doesn't support 8-bit, just only 16-bit. I'm not so sure. I'm gonna make a mental note. Actually, I'll make a physical note too. SPI 2 EFF. Okay, cool. I'll make a note to go through the data frame format and make sure that we end up with the correct one. But other than that, as we have seen, the peripheral is enabled. Um, line 73, could it modify the value after setting? Line 73. Line 73 of which file, Eric? Maybe you're seeing something. SPI 73. Oh, is it? Did you line 73? Yeah, line 73 of which file? It depends. Maybe SPIH. That doesn't. 73 is invalid in SPIDM. Okay, cool. 8 bits 0, 16 bits you on. I might need to be like defining this as mm, 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 mm. Yeah, Eric, I don't see where a line 73 would make sense. Of main, don't see line 73 where we're setting RX, not main 73. Yeah, not really. Not really. Mm, not really. I don't see how that's going to change because we're stepping into that function. That function is this function in it, and this is where all the things are happening, and I'm confused. Okay, that's just one issue, and it's not a really big issue. We can kind of This I have a feeling SPI2. I have a feeling SPI2 has caveats, and that I have a feeling SPI2 might only support. Um, okay, I have a feeling SPI2. Um, I don't know how. I don't know if SPI2 actually supports. This is a deeper issue. Like it's something that I have to quickly go through quite a bit of it, and I think the plan for today is to throw in. I mean, for the purposes of this video, we have gotten what we needed. Um, we will figure out why. We will figure out why the data frame format is coming out as 16-bit instead of um, instead of 8-bit. We will figure that out. That's okay. This should be 8-bit. Yeah, this bit should only be written when SPI is disabled. So we do. That's why. Yeah. So we do all the configuration and then we enable the peripheral. That's why there's an extra line here. We do all the configuration, we initialize it, and then we enable SPI. So that's probably why. But in any case, for this applications right now, this validly that this covers our use case. Um, Although I will come back around full circle and kind of check it out and see if, like, I don't understand why a zero here should just somehow down the line, just when it's passed into this function, which is this function, should just magically be, I mean, we can also just do zero here. It doesn't make sense because I should clear it, but I mean, if we're here, life is for debugging. Life is for debugging. Let's quickly run a debug. And then, I mean, interrupts are not gonna be um, that difficult, so or that involving. Uh, Boom, boom. TFF still comes out as one. Okay, cool. So this is something that we know is going to be some sort of device issue. And I think this is something I'm going to go on the ST forum and try and find out. I'm going to give up on this. I will go and find out this from the ST forum. For now, let's move along. Let's go to SPI interrupts. What the stream is for today. We know the code that we've built so far is working because we're enabling SPI, we're setting it properly, and we can send and receive data. I'll upload. The problem with sending and receiving data is we need two machines or a peripheral and a machine, and then we do that, which I haven't figured out how to show on stream easily. I'll figure that out as we go along. So next thing, let's look at SPI interrupts. Okay, cool. I don't necessarily want to start like from basics. That's not my aim. But if you do have any questions about interrupts, feel free to ask. But basically, interrupts. So applications, the way we are writing them right now, will run in a forever loop. Let's go to our main code, and we can see there's usually a forever loop in your code somewhere. Either all of this could be in a while, or sometimes it's just a while loop to keep the code where it is, to keep the function alive. Like this forever while here is waits for this interrupt, and whenever this interrupt is invoked, this is a GPIO interrupt. Whenever this interrupt is invoked by me pressing a button, the code changes color. So I can actually demonstrate this. Okay, cool. I don't know if this is evident. I don't know if this, I don't know. Can you see this? I'm gonna just pull up my streaming window to see. Okay, cool. So if you observe, there's a button on my breadboard, and then there's two. There's a green LED and a red power LED. And if I press this button, the green LED flips on. And then if I press it again, it flips off. So you see here, it's off. Press it, goes on. Press it, goes on. Press it, goes off. You see? So this is the problem with. I need to figure out my streaming setup so I can stream better. But what I, what I basically am what I'm basically what interrupts are is basically you have service routines or you have functions that can basically interrupt the processor while it's running the main loop, while interrupt your application while it's running the forever main loop. So that way you can get notified of something happening, and then based on your notification of something happening, you can handle what happened, if that makes any sense. Um, the first thing we need to do is to add SPI. Any questions, Eric, especially if you have any questions, because you're always here. So first thing we need to do is to add the IRQ numbers, the interrupt request numbers, to our MCU specific header file. So let's go there. MCU specific header file, and then we'll go to interrupt numbers. Oh, cool. So defined interrupt numbers for SPI1, SPI2, SPI3. I can quickly display this, where this comes from. It comes from the NVIC. We should have a vector table somewhere. NVIC. Nested vector controller. Cool, let's go here. This is an NVIC table. And then we'll go for, I think our line is, our devices are medium. No, okay, so XL. So we're in connectivity and medium connectivity here. So if you look through this is a interrupt and exception vectors. So this is all the interrupts that this MCU supports. So if we look through here, we'll find SPI1 number 35. So that the number on the outside is the number for the thing, and then the second number is a priority. We'll get to the priority is kind of like who can over who what interrupt can overempt overempt is overempt a word overempt preempt preempt yeah, preempt is the word. So like if you get a interrupt to the higher priority than another one, the higher priority interrupt will stop the one that you had. So basically what we need to do in order to include SPI interrupts in our code, we need to find the interrupt numbers for SPI1, SPI2 is 36. I think all the code is here. Sorry. So we have SPI1 35, SPI2 36, and let's go find SPI3. SPI3, it's gonna be somewhere here, 51. SPI3. So we have all the interrupt request numbers for yeah. No, it's not the left shift. It's going to also, if it was a left shift when we did the 0, it should have fixed. I think more is that there's something in the reference manual we're missing that is triggering that thing to go into 16-bit. Or maybe SPI2, the SPI2 peripheral itself can only operate in 16-bit. But we'll get to that. That is something we can deal with not now. We don't have to stop every time completely. Okay, cool. So how do we do this? We need to, number one, we need to add the interrupt request numbers into our code so that our code can identify that we've got an interrupt on that. Okay, cool. That's the first thing we need to do in order to handle SPI interrupts. So to do SPI interrupt configuration is exactly the same as the way we do GPIO interrupt configuration. And luckily, I have some code already for this. So the only the interrupt configuration is how do I say this? Okay, there's two parts of interrupt configuration. You need to configure the interrupt. This means to enable that the interrupt will happen. And then once you configure the interrupt, you do that. Once you enable the interrupt, you need to assign it a priority. You don't necessarily need to assign it a priority because it already comes with priorities. Like this, our file here already mentions priorities. So these priorities are applied. But you can use interrupts the way you want, and you can reassign these priorities the way you want. So the thing is, what we're going to do is we're going to give you a function to enable you to arrange the interrupts in your code as you want. You might want your SPI peripheral to be able to stop your I2C peripheral. So, and I2C might be higher. See, I2C might be higher in a priority, but in your code, you might want that SPI, or in your application, you might want that SPI preempts the I2C peripheral. And this code that we're going to add enables you to do that. I've added a bit of code there. We'll quickly walk through it. SPI RQ configuration flips the value at a given output RQ number. mask. So there's the NVIC, which is our nested vector interrupt. Oh, what is an NVIC? um, interrupt? Yeah, nested vector interrupt controller. Um, the way you use, so it has registers. Where's the NVIC registers? Okay, number one, NVIC registers are going to be mentioned in a different document. If um, if that makes any sense to you. So in related documents. So in the Cortex M4 programming manual, referring to the Cortex M3 programming manual, I'll confuse between M3 and M4 for this because I'm also writing code for an M4 processor. Um, but here's the thing: all Cortex NVICs are the same. You might need to refer to the manual for like details or stuff, but some quite a bit of the code is reusable. So in order to enable um, so let's find out first of all what is NVIC ICR register. It's gonna be easy. Let's quickly you don't need, yeah. It's internet interrupt set enable register. So what is we know exactly what that is. It's a register to registers that enables interrupt. So you need to, it's like 32-bit register, and then in the 32-bit register you need to find out which section you're working on in order to set it. And you can see the calculation here. The reason I'm being kind of very like surface level is because in order to fully explain registers, I have to kind of go through what interrupts are, how to work with these registers, and that takes us to different manuals. And generally, I'm doing this so that I can do this, and I don't want to go to another manual in order to explain it. It's quite easy to go find out. If you have the reference document, if you have the reference manual, which you're going to have, if you're going to be building, if you're going to be writing this code, the related documents will help you find the stuff we need. Okay, cool. So cool. So basically, our MCU supports, I think it's 88 interrupts. Here we can quickly look through this. We just want to look at the NV table. So we are in connectivity line. Cool. Not Excel. Okay, cool. So you see we have 74, and then we'll have like software controlled like timer interrupts, another like another 14 interrupts that can, we have like some software interrupts like 2 or 3, and then another like 12 yeah, actually here 68, and then 16 comes from 68, not including the Cortex M3 interrupt one. So we have 68 interrupts that come on the controller, microcontroller, and then we have like a few more that makes, basically they come up to a total of 88. It depends on the device. Like the larger device you go, the bigger the device. Some of them will go up to like 255, I think. So I don't know. it depends on what device you have and how many peripherals you have and the pinouts and stuff. So what we have to do is take the interrupt number, go to the interrupt set enable register, and then we need to find out which bit. So this enable register is like grouped in groups of like, think about it. If you have 88 things to set, and you're using 32-bit registers, you're going to have to 0 to 31, 31 to 64, 64 to 96, so on and so forth, so on and so forth, until you cover all of them. So we need to find out which set enable register to use. They are 32-bit registers. We find this out by calculating it from the interrupt number. So when we get an interrupt number, we find out where it is, on which register it is, and then on that register, we'll do like some for the sorry, I'm gonna kind of pause so I collect my words and explain myself properly. For the IRQ numbers below 31, we can just use the number of the IRQ itself. However, if the IRQ number is above 31, then we need to like, because there's no like 32nd position in a register. 32 technically becomes 0 in register 2. So we'll do a remainder and then over 32 or over 64 to determine which bit to flip. Okay. And then we can also do a disable after that. So we can enable and disable interrupts. It's good to enable and disable interrupts so that like, even if you're just momentarily, like if you're using like burst of information, use the peripheral and then you're done. It's good to like clean up after yourself. Remember, enable peripherals equals power, enable interrupts equals power. That's clock cycles equals power. We're in an embedded environment where power is quite like limited and we need it. Cool. And then, so IRQ priority config, priority config. So flips the bit at a given value, IRQ number. Okay, so what does this do? It sets the IRQ priority, the interrupt request priority. So then you can have like SPI, it can preempt SPI can preempt SQLC, SPI1 can preempt SPI2. So it depends. It depends on your application. So this sections, the IPRX section register, I think I can probably just Google this. IPRX register ST. Yeah, so there's a register that we use. STM32 interrupt registers. I just basically want to see the IPRX registers mentioned. STMRs. Yeah, so it doesn't make this uses the how. Programmer's model. The problem is I know it's not gonna be in the Bluepill because it will want me to go to the Cortex M3 generic users guide and then okay, cool. So there's the IPR registers, interrupt priority registers. Interrupt priority registers, they're sectioned like that. So each you have like that you have as many as how many um, as many interrupt priority registers, and each register is a 32-bit register. So we just need to and also it depends on the number of number of priority bits implemented. So this one has like 4 bytes, you see. So there's a 0, there's a 1, there's a 2, and there's a 3. So 4. So it has 4 sections, and we need to find out which section to set as how to ensure which register is working properly. It's it's mostly like it's mostly calculating out which position to change. And as you can see here, we get the IRQ number, the one whose priority we want to set. We get a priority. Find out the IPR register to use. So IRQ number divided by 4. So which like which register to use, which section to use, which register, number one, which register, this one, that one, or that one. And then in the second part of our code, we find out which section to use. And then we find out how many shifts, and we do the shift. I don't want to break this down because it's basically breaking down an algorithm of how, it's a formula that like everyone's going to develop this formula by themselves depending on how you end up understanding and implementing um, the interrupt requests from here. Let me know any questions. Let me know if you want, and I can do a deep dive into interrupts as themselves, as a different video. So let me think about it. I can do an interrupt deep dive thing, and that should like kind of clear quite a bit of this. Yeah. The way interrupts work majorly just depends on the silicon manufacturer. So TI is going to have their own thing. Uh, no, I'm wrong. The computing, like ARM defines how interrupts work. And once you get like ARM interrupts, you can reuse them everywhere. It just depends on how the silicon manufacturer configured a few bits, a few more things. Okay, so we'll start with that. So we have to code in to configure an interrupt. And then we also have added code to configure, like we can activate an interrupt now, and then we can also set the priority of the interrupt that we've activated. Reasons for that, we know. Okay, cool. So in order to finish, like in order to get, in order to basically implement interrupts, we need to provide, so if we go back to SPI here, and we look at receive data and send data, we realize that this send data waits for a flag, and then receive data waits for a flag. So what am I saying here? Both of these APIs that are provided right now are blocking APIs. The processor can't go off and do something else while we're waiting for SPI to come in. So with interrupts, since the processor can keep doing its thing, we can remove the blocking APIs. That way, we can interrupt enable us to basically write our code in a way that is not blocking. I think, yeah. Yeah, cool. I'll do. Eric, I'll make your video. I will make your videos. I'm saying Eric because he's the one who's like keeps requesting stuff. I'll make your video on interrupts, like kind of like a deep dive from start to finish. Um, it's like a standalone thing. So basically, what enabling interrupts right now is going to do for us is going to enable us to remove the while loops that you see, we're, we wait for the RX not empty flag to be set, and then we do a receive. So basically, anytime someone calls SPI receive data, we're waiting until the peripheral receive data, and then we can actually consume the data. So what we want to do now is move to API that enables us to just receive or send data without waiting. So not blocking. So this is a blocking API. Or let's implement the non-blocking API, if that makes any sense. Okay, cool. So what do we need to do next in order to do that? Let me think about it. And let's look at our MCU definition header. Let's make sure we have all the. This is wrong. This is OVR. So RX not set, RX not empty, TX empty. These are the flags that we need to use. Uh, Underrun error, master error, CRC error, overrun error, busy, free. We're gonna use, so let's look at the documentation and see how many interrupts SPI has. SPI interrupts, zero peripheral interrupts. Functional description, I think. SPI interrupts. So these are the, okay, cool. Transmit buffer, these are the interrupts that SPI has. Transmit buffer is empty. What does transmit buffer empty mean? We've sent out the data. So we have an event flag, TXE, and we have an interrupt control bit. So transmit buffer empty interrupt enable bit. We have a bit that will enable this interrupt. Receive buffer not empty. What does this mean? We have received something. There's a flag for it, and then there's RX not empty interrupt enable bit. And then we have a few errors: mode F, overrun, CRC error, depends if we're using them. There's also a frame error, but it's only for like TI stuff. I don't know. The TI silicon provider might have a frame error. So there is a few other errors that you might want to cover, and it will depend on the microcontroller that you're using. Okay, cool. So what do we need to do? We need to write code so that we can enable the control bits, and these are in CR2. If you look at CR2, there's RX DMA, TX DMA, SSOE. Let's just actually look at them. Let's look at the documentation, so we can just look at the interrupt with the registers, SR, the ones we're using. CR2. TX buffer not empty, TX buffer empty interrupt enable, RX buffer not empty interrupt enable, error interrupt enable. This will do all the OVR, modef, all of those errors. And then we have SSOE, that's fine for source control. So like enable clock control, but we are only like in simplex mode. TXDMA, RxDMA. This is a bit more complicated. This just means like we can use the direct memory access to send data or receive data. More advanced, we can do this later. It's right now I just want to build a complete, kind of like complete driver, just exploring all of the things. I'm not going to Eventually, we will implement this. Maybe not now, maybe not this week, but we'll probably handle other peripherals before coming back to using SPI with DMA. So cool. Mm, so let's think about this. Let's go to using interrupts. I don't even know if this kind of has to be, this is going to be a thought process. Okay, we've gotten to a place where we actually have a stateful peripheral. Because think about it, we'd like a peripheral where we can hold some state. Because now, if we're going to do things asynchronously without waiting, then that means that we need to hold some state in order for us to process the state. Okay, so we probably need to hold the Rx and Tx buffers, so that's the Rx buffer. So when we receive data, we can put the data in the Rx data. When we're able to send data, we can send data from the Tx buffer. We probably need to hold the length of the data that we are sending, so we send that for it. And then we probably need to hold, are we receiving or are we sending data? So let's modify our code to actually use this. Um, okay, cool. Let's start. So it's gonna be, I think, in SPI.h we'll start there. So let's use this handle so that we can actually state for inter okay, cool. So I think we start with a pointer for PTX buffer, PRX buffer, and then I think this is gonna be TX len, RX len, and then lastly state. RX state TX state. Okay, cool. So that's fine. And then we need to add some states so that we can actually use it. So the SPI states. Excuse me. So define I think this we can set as 0. Okay, cool. So we have states that will we can use. Okay, SPI events. You know? Define SPI event tx complete 0 define one overrun error. Okay, so given these three, okay, and then let's add a few more. Let's add void. Um, so void someone's talking. Luffy? Okay. Yeah. SPI send data with the interrupt. I'm kind of busy right now. Oh, just settle down. Let me finish this and then we can go play. Okay. SPI handle team PSPI PSPI handle, and then passing the TX buffer, probably TX buffer and the length. Yeah. I think that's a good one. You probably can copy that. That way we have all the state. Save data ID handle PRX buffer. Okay, cool. So we've added two kind of definitions for handling data with interrupts. I think we'll need a few more APIs. So think about, we will need an API to handle aborting, you know, and then probably to clear an error, and also probably to abort a transmission, to abort a reception, and to clear, like I wanna handle I would like to handle overrun errors in this code. So since they're the ones I've handled before, and it's enough as so I'll just paste those in. That's fine. I think those should be enough. Those should be enough. Um, I am kind of like taking inspiration from both Kims's and like what other people have done. So some of these things might appear like it's out of the blue, but it's mostly like I do research before I do the stream, so I can answer this. Let's quickly go implement the new APIs that we have described. Okay, send data. So I'll want to implement this new one here. Okay, so let's implement this one here. That's number one. I think it's gonna be almost the same as this. IT. So PSPI handle. Yeah, same. Cool. So let's implement this. First thing, check that SPI is not busy. So this is kind of like, we have to think about it almost opposite the other way we did the other thing. So uint 8. So we basically won't like start sending something until like, you know, PSPI handle dot tx state. I forgot something there. So let's check the state. That's why we read the state in order to know what's happening. Okay, and then here, let's quickly do if state not equal SPI busy. So if we're not busy sending data, we can actually start sending the data. Okay, cool. Else, I guess we wait. And this is actually quite good. So we can change this returns uint 8t. So let's make it uint 8t. Uint 8. So what will happen is if it's busy, it will tell you that it's busy, and then you won't send. But if it's free, it will send and it will tell you it was free. If that makes any sense. Okay. So let's save the tx buffer. So let's hold on to the data we want to send. Okay. So PSPI handle dot tx state tx buffer tx len actually equals len SPI handle dot tx buffer tx buffer ptx buffer, and then we're gonna put this in. We're gonna put it in ptx buffer. Yeah. Okay, we can always take a struct that's already initted and just change that. Okay, cool. Cool. And then we need to do mark SPI as busy. So we start the transfer. PSPI handle dot tx state equals SPI busy. Okay, and then transmit. Well, look at it this way. Now that we're implementing an async API, we won't have the data we're going to send yet. That's why we need to hold on to some state. So what we'll do is we will hand over our SPI peripheral that is set up and ready to be used. And this peripheral will now be used by the service handler, interrupt service. So once we move to interrupt based, an interrupt has to come in. So in the interrupt service routine for this is where we will handle the data transfer. Okay. Enable TXEIE. Basically enable the interrupt that tells us, hey, this data has been sent. Okay. Coming to the interrupts now. PSPI handle. I think SPI config. I think CR2. Dot. Oh, PSPI dot CR2, and then yeah, TX. Okay, so transmission ISR. Okay, that makes sense. So that sends the data. Let's add the receive data IT here. Cool. So let's add the receive data function. I think under this one. Yeah. I want to copy the documentation for this. I apologize. I want to document everything, but I don't want to type out everything. Save for our saving inbound. Okay, cool. This is going to be the same as the other one. We'll basically just build up a SPI that's ready, and then we will hand over. We'll make our peripheral ready, and we'll hand it over, and it can be used. So, but this is going to be. We'll start by here. This is going to be RX state, and then PRX buffer. That's fine. This is busy in RX, and then this is going to be RX len. This is going to be RX, and then this is going to be RX, and then this is busy in RX. This is busy in RX. CR2, TXEIE. This is going to be RX and EIE. Reception now handled in ISR. Perfect. So what does this achieve? This gives us functions that we can use, and this returns a state, returns state. So this is return uint 8t. So basically, you will prepare the peripheral. You prepare SPI peripheral 2. You can actually copy it from an initialized one. So if we go into our main.c, you'll notice that we 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 make a generic handle T here, and then we use it to initialize our each pin differently by changing one part of the struct. So what we'll do is probably initialize SPI, and then once we initialize SPI, we can go around setting it and using it as such here. Okay, cool. So let's now, what do we need to do? Now, what we need to do is we need to do the hierarchy handling. Let's come to the bottom here. So let's now add code to add code. We have like get flag set. Let's now add code to handle the interrupt request, because this is what will happen once we move here. Once we move into interrupts, whenever we want to send data, we'll basically tell the microcontroller, hey, here's the data. Here's the data that I want you to send once we get the transfer, the TX buffer, the TX. Once we get the TX flag that TX is ready, here's the data that we want to send. And once we hand that code over, we'll basically wait for the interrupt, and then once that interrupt is there, we'll use it. So let's write an interrupt request handler that traps interrupts based on based on either the sending interrupt or the receiving interrupt or the error interrupt. It does a different action. So it traps interrupts. Once we get an interrupt that says ready to send, it sends. Once we get an interrupt that says ready to receive, it reads the reception. With received, it reads the reception. Once we get an interrupt that says here an error occurred, we provide a function for that. Okay, cool. So let's do that. I think we have a function for it. I think we have a header file for it. Hierarchy handling. Okay. So, cool. So 1018, that's fine. Okay, let's implement this. Void SPI hierarchy handling. Okay, interrupt request handler. So this will handle our interrupt request. So let's do TX interrupt. You int 18 temp 1 temp 2. Let's have a couple of temporaries to use. Temp 1 is equals to PSPI handle. PSPI, I want this to be a SPI. It's good when things are very clear. Pointed to the SPI handle. It's easier when things are clear, so nothing gets lost. PSPI handle. PSPI handle. I think we're gonna go PSPI rex, PSPI x dot sr. SR, and here we want to check the TXE flag. Okay, let's check if TXE is set. And then temp 2, with temp 2, let's also check, oh no, that's wrong. Let's now check if in CR2, do we have interrupts enabled, or rather do we have the TX interrupt variable? Okay, so if TX flag is enabled, if we're in the interrupt request handler, TX flag is enabled and the TX interrupt is also enabled, then we can take action. We know the flag has been enabled and then interrupt has been enabled. We know, okay, we have some data to send now. Okay. SPI CR2 TX EI. Okay. So if both of these things are, if we are in the SPI RQ handling function, we are an SPI interrupt has just occurred. We don't know which one. Number one, the interrupt, the TXE flag is set, and the TXE interrupt is enabled. So we know that the interrupt that has occurred is now a transfer one. So if temp 1 and temp 2, if these are occurring, we have an interrupt, we have a TX interrupt. So send. Okay, SPI, let's add some functions. TXE interrupt handle. PSPI handle. Okay, let's send the handler to a function that does the sending. Okay, that way we can make it kind of clean. So let's do RX interrupt if, okay, so this is gonna, we can actually just get these and that, copy that, put that here, but we need to change a couple of things. Just source format. Okay, cool. So this is going to be RxNE, okay, and this is gonna be RxNEIE, RxNEIE, okay, and then this is going to be SPI TXE RxNE. Most of these functions will implement, and they will look exactly like what we have. We already have like routines for sending. So I want to handle the overrun flag as an example of an error to handle. Okay, so let's just go here and just copy all of this, and then I want to do this, and then source format. Sorry, covered my mouth. Status register, we need to know if the OVR bit is set. Okay, and then we also need to know in CR2, we need to know if error interrupt is enabled. And then here I would want to go like OVR interrupt. Let's quickly implement those three functions, if that makes any sense. Yeah, let's quickly implement these three functions: TXE, RxNE, and OVR. They're going to be very how do I say? They're going to be very, I want to implement three private functions that are not like used by that will not be available outside this folder. So let's kind of just quickly run through how to make private functions in C. If you know C, we're gonna do this. We're going to go up here to the top of the file after the include. We're going to do that, and we're going to make them static voids. Static void, static void. Okay, cool. So, and I'll just copy all of this again. So static void basically enables us to static void will make sure that if at all these functions are called outside this, if at all these functions are called outside this file, then we'll get a compile error. And so we basically will not, the user will not be able to do this. The code in TXE interrupt handle uh, is exactly the same as this block of code because it's kind of exactly the same as this block of code, this one. So all we do is like if basically yeah, just this send data, and then we'll also add some we'll add some we will add some um, we will add some a bit of we will add some more kind of overhead stuff to make sure that we clean the state and things are good. So let's do that. And then open, quickly format that. Source format. Cool. I'm gonna quickly check my comments for anything. None. Eric, commendable for still being here, watching me fumble over my words. It's been a few years. Okay, cool. So once we've sent, we should do all the garbage collection. We should close the peripheral. We should be what's the word for this? Elegant. Once we've done this, we shouldn't leave a hanging peripheral, hanging pointers, and all of that stuff. Let's close the peripheral, and once we close the peripheral, we can like, we know we're leaving this done. Okay, cool. So let's check if the sending is done. How do we know if sending is done? So PSPI handle dot tx dot. Oh, this means it needs to be fixed. And it's fine. It's fine. Just a moment. And go to the top. Let's change that. I don't know. Would you do all of this work before committing? I don't know. I don't know. Right now I'm just coding, so I'm not even thinking about a PSPI handle. Okay, dot. I think it's if TX length is done, if there's no TX length, we are done. Cool. And then let's call SPI. I think we added some closed transmission. PSPI handle, that's fine. We haven't implemented these, so don't worry about them yet. And then here, if PSPI dot rxlen, this should be a not, and then we should do that SPI closed reception. Cool. Be clean, be nice, do that. Let's now handle an overrun error. So if an overrun error occurs, we do want to let the we want to we want the application that is using SPI to know that an overrun has occurred, and so we need to inform the application. But also, when an overrun occurs, uh, if you look at the documentation, what happens is the new data that is received. So overrun occurs only like when the RX buffer still has some data, and then we still receive, and then the RxNE flag is set again. When the RxNE flag is set again, an overrun error occurs. The new data is discarded, and the data is then and the RX buffer is still held so that we can read it. So what we need to do is clear the overrun flag, but tell the application that an overrun flag happened. But we won't affect the data so that they can finish reading on them. Okay. Clear OVR flag. The way we clear the OVR flag is by reading a couple of basically reading a register. If we read the status register, we should be able to clear it. SPI handle dot tx state not equals SPI busy in tx. So if we are not busy in transmission and an overrun flag occurs, we will do temp equals SPI PSPI handle dot PSPIX dot DR. Okay. Yeah, just read them. If you read these registers, the overrun error will occur, will disappear, and we can move on with life. Okay, we will modify them so that they can actually, let's use that variable so that the compiler does not complain. Okay, cool. And then let's add application. Let's add an application callback. This callback is for the application to know that something is cool. Yeah. So an overrun error occurred. That's cool. And then let's also go ahead and do a weak implementation. Weak. So let's add an attribute. Let's add how we call it. You see the way we've defined volatile here. Let's define another one. Define weak. It's weak. It's attribute weak. I think that's the one. I think that's how if I'm not wrong, that's how you make I just need to read some code somewhere. That way attribute weak. Yeah, okay, cool. So this on this. Okay, cool. So and then we go back to our SPIC file, I think. Take SPI. No, then this is in okay. SPI handle team PSPI handle PSP PSPI handle, and then this will take you int 8t app event. Weak implementation for application to override. Okay, cool. Let me think about this. Is there anything else we're missing? We've added receive data. We've added send data. We need to add the closed transmission, and I think closed transmission and clear overrun flags. We need to add those. We need to add, yeah, we need to add a couple of implementations before our voids. So there's a couple of functions we need to add that we declared in the header void SPI define SPI. Yeah, we called, you remember, we called closed transmission, closed reception, and I think clear overrun. So let's add some functions to do that. SPI, I want to go to the header and just get the files that I want. These. Okay, cool. So that I can just implement them here. These helper functions. Come on. Last stretch. And we're done with int 8_t temp. So to clear the overrun flag, we need to do temp equals PSPI handle dot PSPIX dot dr PSPI handle dot PSPIX dot sr, and then we need to void temp. Cool for using it. And then let's go to the next one. Close transmission. What do we need to do? Close transmission. Reset the state. Reset the state and tell the application. So we need to go back to a state that will enable us to do the next transmission. So PSPIX dot CR2. Now we're going to check so let's reset CR2 1 SPI CR2 to TXCI. Just what did we do there? We reset the interrupt for TXE. So now someone else can use it. PTX buffer. We need to add a header for that. Handle dot txlen equals 0 PSPI handle dot txstate equals SPI ready. Gracefully finish TX and reset to sane state. Okay, SPI ready. And then the next thing we need to do is SPI application, event callback, PSPI handle, and then this is going to be SPI event event TX complete. See what just happened? So we finished we did all the closing work, just like there was an open socket basically to like handle this gracefully finish RX. So this way, when everything is done, like you don't have like hanging states and stuff. CR2 equals 1. So we're resetting this so that SPI CR2 RX NEIE, so someone else can use it now. And then PSPI handler dot px buffer prx buffer equals to null PSPI handle dot rx len is equals 0 rx state dot SPI ready cool, and then SPI application PSPI handle SPI event rx complete. Okay, cool. So what else do we need to do? Let's add an application callback to our SPI header file. Okay, cool. And then let's build this thing. A lot of errors. Okay, SPIH. This on this thing. Okay, cool. Let's fix number 254. No. Okay, let's build that again. Yeah. Yeah, my cat's scared. Oh, now. So in order for null to work, we need to add some definitions to the. We need to add. I think we need to add standard definition so that null works. So let's add it here. Oh, sorry. Okay. Ah, 441. Go lower. Sorry, guys. My house is 449. Ah, okay. See, it will end. It will end and you won't die. Sorry, guys. I just quickly walking through these implementations and just fixing one by one. So that V, that V, that V, 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 V. I'm quite sorry about the noise. Ooh, yeah, cool. So what did we just do? Basically implemented interrupts for I squared C. There you go. This is amazing. This is the end. So this is the last stream for you. I skipped ahead. This is going to be the last stream for SPI at the moment. I think we have a basic implementation that kind of showcases how SPI works, how to implement something for SPI with interrupts, without interrupts, and kind of get something working. Next week, and maybe the next 2 weeks, I'll be working on I squared C, and we'll see how that goes. Yeah. So I'm gonna do some comments here, and I'll push this up, and I'll see you guys next week. I'm quite tired. That was actually a 2 hour stream today. Very difficult, but quite exciting. I'll work on how I explain things more, and be sure to leave me comments. Tell me what you need. Subscribe, like. That really helps. It really encourages me to keep doing stuff. So thank you. Cheers, people. Cheers, Eric. That was amazing. I'm gonna stop streaming, commit this work, and push it up to GitHub.